All right, guys, so we kind of get to start having a little bit of fun. 3.8 is all about optimization. And whenever we hear optimization, what we're usually dealing with are story problems. And we're usually looking for the largest or smallest value of something. And what makes this one interesting is this is where we start putting the applications of calculus into the real world, because you might be trying to maximize your profit at a factory. You might be trying to minimize your expenses for wages with your employees, or your expenses with product that you're using for development. This maximizing and minimizing is something that physicists use. It's something that scientists use. It's something that they use in the medical field. It's something that we use in business all of the time. Because if you can put an equation together to represent something in the real world, you can maximize or minimize. You can find the largest and smallest values for that function using calculus. So all we're doing today, I think we've got 3 story problem examples for you. And we're going to be trying to set up an equation. So the steps right here, you can write them down if you want, but this is just kind of what we're going through. We're assigning symbols to different things in the story problems, variables that we're using to determine the quantities. You can make a sketch if you need to. We're writing an equation that we're going to use that we want to maximize or minimize. So if we want to maximize the cost, we need to write an equation. I guess we would never want to do that. If we want to minimize the cost, we would write an equation and that involves cost. If we wanted to maximize distance, we would write an equation involving distance. We reduce that equation so that we have one variable. We really don't want to do implicit differentiation with these problems. So we might have to come up with a second equation to help us eliminate a variable. And this may have to use, we almost always have to use a second equation. Then you determine the domains. It always makes sense. You've got to look at what values make sense in the problem, okay? If you're looking at the domain of workers, it doesn't make sense to have negative numbers of workers, and it doesn't make sense to have 1,000 workers in your business. What values would make sense for your domain? And then we find the maximum or minimum using our calculus techniques. So remember, we take our function, we find the derivative of our function when it's equal to 0, when it doesn't exist, and our endpoints. And we use those values, we use those critical values to plug back into our function to find out what our maximum or minimum is, depending on what it is that we're looking for. So let's give this a try. We're going to avoid the calculator when possible. I've got it pulled up just in case we run into something that we get lazy and we don't want to plug in. But most of these, I think that we can handle the work ourselves. So it says to find 2 non-negative numbers, x and y, whose sum is 60. So it wants me to find an x and a y that add up to be 60. Now it says that they're non-negative. So that tells me something about my domain. The smallest it can be is 0. And it's got to go up from there. And let's see what else it tells. Well, and if they add up to 60, the largest one of them can be is 60, right? If they're going to add up to be 60, one of them can't be more than 60 because we're only using positive numbers. Or I guess we're using non-negative, so 0 is an option. And it also tells us the product x and y squared, so x times y squared, is a maximum. So that's what we're trying to maximize, this product. So let's make that a function. Let's call that g. I don't know. So we're trying to maximize our product based on the fact that the 2 numbers we're using add up to be 60. So since this is what I'm trying to maximize, that's what I'm going to take the derivative of. That's the first thing we got to be careful. We have 2 functions. We want to take the derivative of the one that we're trying to maximize. So that would be this g function. You can call it whatever you want. that's going to be this g function. You can call it p for product or f, or just, it doesn't matter what we call it. So the first thing that I've got to do is get rid of one of these x's or y's, because I don't want to do implicit differentiation. And if I look at this function, if I'm trying to get rid of x or y, if I figure out what y is, if I solve this equation for y and plug it in, I'm going to have to square it, and I don't want to. So I'm going to choose to solve for x, just because that's going to plug in a little bit easier. So to solve for x, I minus y from both sides, so I just get 60 minus y. That becomes my x value. And then I'm going to go ahead and plug that in for x. So my g function becomes, instead of x, I get 60 minus y multiplied by y squared. So when I distribute that, I get 60 y squared minus y cubed. So that's not too bad of a function. 60 y squared minus y cubed, I can work with that. So derivative time. I take the derivative of g. So 60y squared becomes 120y. And then negative y cubed becomes negative 3y squared. So still not too messy of a function that we're working with. And that's it for my derivative. So my values that I'm interested in, remember, to maximize or minimize, we want to know when our g prime equals 0, does not exist, and we've got to check our endpoints just to be sure. That's a step a lot of people skip, because usually, and we know this, because if I'm maximizing product and one of my values is 60, that's going to give me a product of 0, which is definitely not going to be my maximum. And if my other value is 60, then my first value, these go together. If one is 60, one is 0. So I know that my endpoints are just going to give me a value of 0. They're not going to be the maximum, but we have to include them when we check, because sometimes our endpoints are our maximums. In this case, it wouldn't make sense for them to be a maximum. We know it's not going to happen, but we'll check them just to say that we did and make the AP test people happy. So what we got to look for, anywhere that this doesn't exist, because I don't have a fraction with a variable on the bottom, I'm not really worried about it not existing. I do need to check when it equals 0. So if 0 equals 120y minus 3y squared, I've got to factor out a 3y. Hopefully we're getting better at this part, because we've been doing it over and over and over again. Anytime we're looking for something that equals 0, we're going to factor to try and use that 0 product property, right? So 3y can equal 0, which means that y could be 0. Or 40 minus y could be 0, which means when I add y to both sides, y could be 40. And just knowing a little bit about number sense, we already know that if y is 0, these are going to multiply to be 0, and it's probably not going to be the maximum, but it wants us to check. So I've got my values. I've got my 0, my critical values. I've got my 0 and my 40 and my 0 and my 60. So for, let's see, we are plugging in y's, right? So we're going to plug these into G. So I'm going to plug in 0, I'm going to plug in 40, and I'm going to plug in 60. So when I plug 0 in for y to my G function, we've got to use this G function right here. We don't want to use the one with the x, because I don't know what my x's are. So we're going to use this one right here, 60 times y squared minus y cubed. So if I plug in a 0, I just get 0, which is exactly what I would expect. So that's not going to be good. If I plug in a 60, right here I get 60 squared times 60, which is just 60 cubed. And then I'm going to minus 60 cubed. So I'm going to also get 0 when I plug in that value. Now, when I plug in a 40, that's not one I want to do in my head. So I'm going to take 60 multiplied by 40 squared minus 3. Nope. Yes, 60 times 40 squared minus 40 cubed. See, we're not going to make any mistakes today plugging stuff into the wrong formula. We're plugging it into our G formula right here. So 32,000 would be my maximum. Okay, so this value gives me a maximum for sure. I checked those, 0, 0. This is going to be a maximum. But it wants to know, it doesn't want my maximum, right? It doesn't say what is the maximum. It says find two non-negative numbers, x and y. Well, I know my y value. If y is 40, then what is x? So if y is 40, I just go all the way back up here. If y is 40, what's my x value? Well, they add up to 60, so that means x is 20. So those would be my two values. Now, on the AP test, we've got to go one step further. Remember that when we found critical values and those relative extrema, those were possible extremes. This 40 is a possible maximum. But we don't know that it's a maximum without checking one of two things. We either need to check the left and the right of our derivative. We need to check that on the left it's a negative and on the right that it's we need to check that on the left, I shouldn't have put left and minus and plus. We need to check the left and the right of 40. Because I need to see, to be a maximum, to the left of 40, I need to be increasing. And to the right of 40, I need to be decreasing. I need to have that maximum. So I've got to have I either need to check that derivative, or if I use the second derivative test, remember, if I check G double prime, if that value, if G double prime of 40 is greater than 0, our second derivative test tells us then that makes it a minimum. And if G double prime is less than 40, then, no, let's see. Yeah, that makes it a minimum. This one makes it a maximum, right? So to me, I already have the derivative. I've already plugged. I mean, it's really sixes which one we use to check. The second derivative of this would actually be pretty easy because G double prime is just 120 minus 6y. So when I plug in 40 right here, I get 120 minus 240, which is negative 120. So I'm less than 0, which tells me that it's concave down, which means that it's a maximum. So by the second derivative test, so on the AP test, you would have to say, here's the values, and you could say by the second derivative test that it's a maximum. But you have to show that you've proved that that critical value is actually a maximum. You could have used the first derivative test and shown the increasing and then decreasing, or the second derivative test to just show that it was a maximum. Either one works, okay? But be careful of that step. A lot of times we skip it just because it seems unnecessary, because it seems obvious that this would be a maximum. But it doesn't always let you just assume the obvious. All right, so moving on. A manufacturer wants to design an open box having a square base. Okay, so I've got a box, and I'm going to have a square base, which means if this is X, this is X. All right, and it's open. So I don't know how many story problems you've done involving boxes, but an open box means that it does not have a top. So it only has the sides of the box and the bottom. The top is open, kind of like a crate would be. There's no lid on it. And it has a surface area of 96 square inches. So what dimensions will produce a box with a maximum volume? So we are trying to maximize volume. Well, so for volume, I know that I take the base times, well, and maybe we should write this a different way. I take the length of the box times the width of the box times the height of the box to get my volume. And in this case, my length and my width are the same. I called them x. So my volume is just x squared times the height of my box, which I don't know what the height of my box is. But this is what I'm trying to maximize. Obviously, I have another variable, this height, that I need to get rid of. Or I can get rid of x. I think the height's going to probably be the easiest to get rid of. But to do that, I need another formula. Now, it tells me the surface area is 96. And to find surface area, I just have to add up the area of all the surfaces. So the bottom surface is just x squared. And then I have to add that. There's no top, so there's only an x squared. Then I have to add the sides of the box. Well, each of the sides is x across the bottom, and the height is h. So I'm going to add x plus h, but I'm going to add that 1, 2, 3, 4 times. I'm going to add 4 x plus h's, and those are going to add up to 96. So with a little bit of algebra here, we are going to say, or not x plus h. What am I doing? X times h. 4x times h plus x squared equals 96. So to get h by itself, let's rewrite this so you can read it. X squared plus 4xh equals 96. I don't want to add those. I'm multiplying to get the area. So I'm going to minus x squared from both sides. So I get 4xh equals 96 minus x squared. And then I'm going to divide by 4x because I want to get h by itself. So h equals 96 minus x squared divided by 4x. Oh my gosh. Okay, so now that I know h, we're going to plug that in to my volume. Volume equals x squared. Instead of h, I'm going to put 96 minus x squared, all divided by 4x. So to clean that up, I'm going to go ahead and distribute the x squared. So volume equals 96x squared minus x to the fourth, all over 4x, which is kind of nice because now my volume equals, an x cancels, so 96x minus x cubed, all over 4. Okay, now I'm finally ready to set up to take my derivative of my volume. The way I have it written right now, I'm going to have to do a quotient rule. So I'm going to cheat a little bit. This divide by 4, I'm going to rewrite this as 1/4 multiplied by 96x minus x cubed. Because that's just a constant out in front, when I take the derivative, I can just leave it out in front. So my volume derivative, I've got 1/4 out in front. The derivative of 96x is just 96. And the derivative of negative x cubed is negative 3x squared. And now if I times that 1/4 back in, 1/4 of 96 is 24. And this becomes negative 3/4 x squared. That's going to be my derivative. And I feel okay with that. That's not a bad derivative. That's not too ugly to work with. That's a lot better than if I had tried to, you can do the quotient rule right here. The nice thing is the derivative of the bottom is just 0. So some things are going to cancel out. And then you're going to end up with a 16 on it's just a lot of algebra. Whereas this just, all I have to do is times by a 4th. That's not too hard to do. So in order to maximize, I've got to take my derivative, and I'm looking for where my derivative equals 0, where it does not exist. And I should be checking my endpoints, but kind of like our last one, my volume is a multiplication. And theoretically, I could make the bottom really, 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 really small, basically 0, and it be a really tall object. Or I could make the bottom really, really big and have the height really, really small. So we could check the endpoints, but we know they're not going to be the right values. If I wanted to check them, my smallest endpoint, because the bottom has to be a square, and what do we need to know? What's the smallest? See, I don't even think we need to worry about plugging these in, because technically we could make the bottom, we could go from, it could be a 1 by 1 and it could be 96 tall. Well, no, it wouldn't. If this was 1 by 1, the bottom would be 1 and the outsides would be 24. Or we could make it really big. We could make it the square root of 96. And it could just be 1 tall. So we'll play with that one just a little bit. Is the square root of 96 right? The tallest that it could be, or I guess the biggest that our bottom could be, so that we had a height of 1. If our height was 1, we're going to have a surface area of whatever our x is plus the bottom. So our surface area, I don't think we need to check the endpoints. I think we're okay on this one to not, because really our whatever endpoint we come up with is going to make the height almost 0, which is going to make our value really, really small. So we don't need to worry about the endpoints because they're going to be insignificant. We'll focus on where this is equal to 0 and where it doesn't exist. Well, it exists everywhere. It's just a polynomial. Let's check where it equals 0. So 0 equals 24 minus 3/4 x squared. I'm going to add 3/4 to this side. And then the opposite of timesing by 3/4 is to times by 4/3. So when I times this side by 4/3, x squared is going to equal to 24 divided by 3 is 8. 8 times 4 is 32. So x squared equals 32. So x is going to equal the square root of 32 or the negative root of 32. Now, it wouldn't make sense for my length of my box to be a negative, so I'm not even going to consider that value. The value I'm going to consider is this one, root 32. So I need to plug that value in. That's one of my critical values that I need to plug back into my volume function, which my nicest volume function, I don't know if nicest is the right word to use, but any of these functions right here are going to simplify just fine. So I'm going to plug in root 32. So I'm going to go ahead and go 96. Actually, maybe, we're okay. We're just dividing by 4. 96 times root 32 minus root 32 cubed. So let's go root 32 raised to the third power. Whoa, what happened? Delete that. That's what happened. Root 32 cubed. I'm going to hit enter, and then I'm going to divide that by 4. And I get a volume of 90.509. So if this was the AP test, if I round to 3 decimal places, that's going to become 510. 90.510 is my maximum volume. Is that what it wanted? Just what dimensions will produce a box with maximum volume? So it doesn't want the volume. It wants my base dimensions. My base is going to be, my dimensions are my length, my width, and my height. So my length is root 32. My width is root 32. So to figure out my height, remember volume is length times width times height. So I can just go ahead and, and my length and my width are, if we go back to this volume function, volume equals x squared times h. Well, my x is root 32. So my volume is root 32 squared times h. So that's just volume equals 32 times h. So all I have to do is divide my volume by 32 to get my height. So this is my volume. I'm going to divide that by 32. And my height's going to be 2.828. So my height is 2.828. So those would be my dimensions. Now, on the AP test, we would have to prove that this isn't just a critical value, but it's actually an extrema. We have to prove with either the second derivative test that that is a maximum, or with the first derivative test, we have to prove that that's a maximum. So if I were to plug in something, the root 32, something smaller than root 32 would be the square root of 25, which is just 5. Something bigger than the root 32 would be the square root of 36, which is 6. So if I just plug in a 5 and a 6, what I'm looking for is I need the 5. I need my my volume derivative of 5. I'm hoping is a positive. And my volume derivative of 6, I'm hoping is a negative. So my volume derivative, this is, remember, my first derivative test. I'm just trying to prove that root 32 is the maximum. So if I plug in a 5, I've got 24 minus 0.75, and my x value is 5 squared. 0.75 times 5 squared. We better write this correctly. There we go. So that's 5.25. So that's a positive. Okay. Now, if I plug in a 6, 24 minus 0.75 times 6 squared, I get a negative 3. So to the left of root 32, I'm positive, which means I'm increasing. To the right, I'm negative, which means I'm decreasing, which makes root 32 a maximum. So I would say by the first derivative test, root 32 is the value for the maximum. So it's not the maximum, it is the input. It's the x value for our maximum, right? So we know that this volume is actually a maximum volume because that increase and decrease. And if you're confused about that proof, we'll talk about that one a little bit more in class. We'll talk about having to show that. It's not hard to do. You just have to make sure that you acknowledge that that is happening, okay? All right, let's do one more. Which points on the graph are closest to the point 0, 1? So it gives me I don't even know what this picture is. We're going to ignore that picture for a minute because we're not using a picture, we're using a function, right? So which of the points on the graph are closest to 0, 1? Well, what's happening here, my graph 1 minus x squared is just a parabola. It's upside down and it's shifted up 1. So I've got a parabola like this. And we're going to have to change that point. Let's change that to 0, 0 because 0, 1 is actually on the graph. So I have this parabola and I want to know which point on the parabola is the closest to 0, 0. Which one is closest to the origin? And it may not be what you think it is, this is a good question for that because the assumption may not actually be true. Which point is closest? Which means I'm trying to minimize distance. I want to minimize my distance. So, distance formula. Do you remember what that is? Square root of x2 minus x1 squared plus y2 minus y1 squared. We're just doing the Pythagorean theorem, but we're solving for the hypotenuse, remember? The minimum distance, this is my distance formula that I want to minimize. Now, my issue is I have a whole bunch of x's and y's. We can get rid of some of them because I know one of my points. It's 0, 0. So I can plug a 0 in right here, and I can plug a 0 in right here for my x and my y. But I have another x and another y, which is no big deal because I have a function. It gives me another equation right here, y equals 1 minus x squared. So I know what y is equal to, so I'm just going to plug that in right here. I'm going to plug my y equals 1 minus x squared, and this x can stay my variable. So my distance equals the square root. My x2 just becomes my regular x minus 0 squared, plus my y2, I plug in that 1 minus x squared, and then I'm going to minus 0 squared. So when I clean this up a little bit, I get the square root of x squared plus 1 minus x squared minus 0 is just 1 minus x squared squared. And if we clean that up a little bit more, I end up with the square root of x squared. 1 minus x squared squared becomes what? 1 squared minus 2x squared plus x to the fourth. You can do that by foiling if you need to, but trust, that's what it comes out to. X squared minus 2x squared. Actually, let's rewrite this. Let's put x to the fourth in front. So that takes care of that. Negative 2x squared plus x squared just becomes negative x squared. And the 1 squared just becomes plus 1. And I'm okay with that, the way it is. So there's my distance formula in all of its messy glory. Now that's what I'm trying to minimize. So I've got to take the derivative of that formula. Okay, so d prime. First thing that I'm going to do before I take the derivative, let's rewrite this. X to the fourth minus x squared plus 1 raised to the half. So when I take the derivative, that 1/2 comes in front. The x to the fourth minus x squared plus 1 stays on the inside, and this becomes a negative 1/2. And I've got to multiply by x to the fourth. Oh, I've got to multiply by the derivative of the inside. So I need to multiply by 4x cubed minus 2x. So that looks like a great big mess. Now we can use, I'm wondering if we can use a little bit of number theory here, because what this actually comes out to is 4x cubed minus 2x all over 2 root x to the fourth minus x squared plus 1. So that's what my derivative comes out to be. Now, one of my options is to use that derivative, which is probably what I would do. I would find, when does my derivative, when is it going to equal 0? When is it going to not exist? And of course, I've got to check my endpoints, which on this one, our endpoints are clear down here to the left and to the right, which are obviously nowhere near. We don't even have an interval to check over. So we don't need to check our endpoints. But when I set this equal to 0, the bottom's just going to go away. Okay. So and I kind of want to show you why I like the shortcut for this one, but it bothers me if you don't see what happens. Okay. So this bottom, if I say 0 equals 4x cubed minus 2x divided by 2 root x to the fourth minus x squared plus 1. When I set this equal to 0, I just multiply that over. I'm just going to multiply that over to the left, which is going to turn it into 0. So I just end up with 0 equals 4x cubed minus 2x. So that's all I'm setting equal to 0. And if you notice, that's just the derivative of the inside of the square root. Okay, that's just the derivative of the inside of the square root. Now, the other thing I need to check for, well, if I finish this through, I would factor out an x and get 4x squared minus 2. So I would check when x is equal to 0. And then I need to check 4x squared minus 2 equals 0. So I'm going to add 2, divide by 4, which is going to become a half. And then I'm going to take the square root of a half. So x would also equal root 1 half. Okay, so those are my two zeros. Now, the other point that I'm worried about would be when this denominator of my derivative was equal to 0. So I would worry when 2 over root x to the fourth minus x squared plus 1 was equal to 0. Well, if I divide by 2 and square 0, I just end up with x to the fourth minus x squared plus 1 equals 0. So I get x to the fourth minus x squared equals negative 1. Now here's the problem. Well, maybe not yet. Let's go ahead and factor this a little bit. So I get x squared times x squared minus 1 is equal to negative 1. All right, so when I square x, I'm going to get a positive. And here, when I square x, I'm going to get a positive. But then I have to minus 1. So in order to solve, and maybe we just need to, right here, if we plug this into our, and showing you this is taking longer than we would like to, but I think it's something that you need to see. So when I'm going to go with a order root 4. I just want to show you what my, what I'm going to end up here. So my a to the fourth is just going to be 1. My a cubed is 0. My a squared is negative 1. My a to the 1 is 0, and my a is positive 1. So when I solve this, notice how all I end up with is imaginary numbers, and we're only dealing with real numbers. So there is nothing that's going to go into the bottom that's real that will make it equal to 0. It doesn't happen. So all I end up checking is whatever makes the top 0, which was the derivative of the inside. So if you think about, if you go all the way back to our function, our distance function, I'm trying to minimize the square root of a number. Well, if I can make that number itself as small as possible, the square root is going to minimize as well. Whatever, I just need to get the smallest number possible on the inside, because the square root of the smallest possible number is going to be the smallest possible number. So I really don't even have to worry about this square root. I could have just minimized the inside of the square root and bypassed all of that checking. But you have to take a little bit of a leap. And on the AP test, you would have to argue that minimizing the inside of the square root would minimize the square root. You would have to show that. Or you can just take the derivative of the whole thing, show that here's my critical values, and here's why the bottom is never going to equal 0. So these are the only values that I actually need to check, okay? I've got 0 and a half, and actually, when I square rooted, I've got a negative root half. Don't forget that negative. X equals negative root 1 half. So in the long-winded way, you could have just used the inside and minimized it if you want to, as long as you say by minimizing the inside of the square root, I'm minimizing the square root itself. We didn't do that. We just took the derivative of the whole thing and showed those pieces, which is okay with me. So critical values. Now that we've ran circles around for 10 extra minutes, I took the derivative. I found my critical values. Let's go ahead and plug those in. So my critical values are 0, negative root half, and positive root half. And I'm plugging those into my distance function, guys. I'm not plugging them into my derivative. Remember, I'm trying to minimize my distance. So my distance formula, let's go ahead and just put it in here. So second square root, I've got, where did we simplify it the most? The square root of x to the fourth minus x squared plus 1. So when I look at the table, I want to look at 0. I want to look at negative second square root of 0.5. And I want to look at positive square root of 0.5. Whoops. Why won't it let me plug in? Oh, I guess that gives me a negative value. So that one we're not going to have to worry about. Whoops, second table. That one we're not going to have to worry about. So let's just plug in, where am I? 0.5. Square root of 0.5. Oh my heck. Square root 0.5 is 0.866. Okay. So let's see. This gives me 0.866. 0 gave me 1. Now this negative 1/2, if I go back to, let's see why, if I try to plug in, oh, come on. What are we doing? If I plug in a negative, if I get a negative here, I get the negative to the fourth minus a negative plus 1. So is it telling me that that is going to negative second square root of 1/2? Oh, I must have just typed in something wrong. So my negative root half is 0.866 as well. So think about your unit circle for just a minute. That one right there, these two answers might make sense. My minimum distance actually happens twice. It happens when x is, let's see, negative root half is at about 0.7. So it happens at 0.707 and or at negative 0.707 and at 0.707. So it happens right about here. That's going to be my minimum distance. What did it ask for? Now that we're way off the beat path, which points on the graph are the closest? Okay. So it doesn't just want the value. It doesn't just want the value, the minimum distance. It wants the points that are the closest. So I've got 2 of them. One of them is negative 7.07. And that gives me a y value of 0.866 and 7.07 or oh my heck, negative. I'm just writing all kinds of nonsense. It must be late or early. I'm not sure which one. Negative 0.707 and 0.707 give me 0.866. So these 2 points give me my minimum distance at these points. And I have all the math shown to back it up, right? Do we need to check that those are actual minimums? We would probably want to look to the left and right of those values and make sure that they're minimum and maximums, or we could use the second derivative test. Either one is going to work. And we can talk about that in class.